Welcome everyone. In this video lecture, we will solve a GATE 2013 question which is based on the channel length modulation effect. Okay, so the question is in a MOSFET operating in a saturation region, the channel length modulation causes option A an increase in gate source capacitances, option B a decrease in transconductance, option C a decrease in unity gain bandwidth product, and option D a decrease in output resistance. So here a MOSFET operating in the saturation region. So I have made a MOSFET, okay, which is basically our NMOS, where we are taking P-type substrate, okay, or we can make like this NMOS, okay. So this one is gate, drain, and source, okay. So it is clearly mentioned when MOSFET is operating in the saturation region, it also causes the channel length modulation. So ideally, the ID value in saturation, so I am writing saturation, okay, when we are not considering the channel length modulation, that is our lambda value will be 0. So the equation will be mu n cox w by L VGS minus VT whole square. Okay, without channel length modulation. This one without channel length modulation. Okay, but when we will write the same equation, ID in saturation with lambda, when lambda not equals to 0, means we are just considering the channel length modulation. So the equation becomes cox w by L VGS minus VT whole square 1 plus lambda times del VDS. Okay, so this one with channel length modulation. Okay, in my in my one video I have already mentioned or derived this formula. Okay, so everyone knows this one. Okay, so if we draw the transfer characteristics or IDVDS curve, okay, so I am just drawing the IDVDS curve. This axis is in ID, the horizontal axis, and the horizontal axis VDA. So if we plot the IDVDS curve, okay, so this one for lambda equals to 0 when we are not taking the channel length modulation. Okay, there will be some curve like say curve shape, and this region is our saturation. Okay, and this one is our, let's say, linear region. Okay, and this point is VGS minus VT. We know all this thing. Okay, so now this one, the one can write this ID or this whole term, this mu n cox, I am writing as a k. Okay, VGS minus VT whole square with lambda equals to 0. Okay, this curve, and for ID when lambda not equals to 0, it is somehow k times VGS minus VT whole square 1 plus lambda VDS. If we plot this one with channel length modulation, so it is found that it have some slope. Okay, so in this case, the RDS value, that is our del VDS by del IDS. In case of saturation, there is no change in the drain current, so this value will be del VDS by this value will be 0. Change in drain current will be 0. So the resistance, drain to source resistance is infinity. So RDS value is infinity. But in that case, there must be some slope. So RDS value will have some finite value. Okay, RDS value have some slope, so it have some finite value. Okay, in RDS, when lambda not equals to 0, okay, this have some VDS and IDS, so it have some finite value. So this finite value or this one RDS at lambda equals to 0, so we can say that the RDS value, the RDS value with lambda equals to 0 will be always greater than this one. Okay, so what we observe that the output resistance, the output resistance will be always lesser or decreases as the increase in the means drain to source voltage. So in the case of channel length modulation, the output resistance will decrease. So our correct option will be option D. Okay. So the correct option is our option D. So in other words, or we can also mm, we can draw this one. Suppose this one ID in this one ID for lambda not equals to 0, we can say this one is some more factor, say k dash 1 plus lambda VDS. Okay, so we can say k dash some constant. Okay, by keeping VGS is some constant value, VT by taking some constant value. Okay, so I am writing this k dash plus k dash lambda VDS. So this one, if we plot, so ID equals to lambda VDS. A line passes through ID equals to k dash lambda VDS. If we add some constant term, it will go up by k dash unit. Okay, k dash. So it have some slope. Okay, so that one is our lambda not equals to 0, and when a straight slope is comes, it should be our lambda equals to 0. So the output resistance always decreases in case of the channel length modulation. Okay, or in more general, we have found that if we have a n MOSFET, okay, so if we draw the a small signal model, so what we are doing, this one is gate and this one is our source and drain, and this one GM VGS. The output resistance, nothing is there. So we are taking R naught equals to infinity, where the channel length modulation is 0. But when we are taking some channel length modulation concept, okay, so this one will be GM VGS. There is no change in GM, okay. But we are adding some finite resistance R naught. So this one is our VGS, gate, drain, and this source. So this one we can say, when we are considering channel length modulation, there is some finite output resistance, and in this case, it have infinite output resistance where we are neglecting channel length modulation. Okay, without channel length modulation, and this one will be with channel length modulation. So we can say the finite output resistance will be decreased. So the our correct option is option D. So this is all about this question. So no need to think about the transfer reactance unity gain bandwidth in this question. So I hope you can understand this question through this concept. And for more details, you can follow my earlier video for the channel length modulation based numerical. Okay. So thank you for watching.